just recap what we did yesterday. So I started with the Liouville theory defined on strip, and then I computed the classical solutions of this Liouville theory and organized them, categorized them in 3 particular classes depending on their behavior under monodromy around the circle on the strip. Then I performed a particular kind of field redefinition in the path integral of the 2D Liouville theory, and rewrote the Liouville action in a particular form in which the action resembles a Schwarzian action. And then I took a classical limit of this action, and my argument was that if I take the classical limit of this action and performs a dimensional reduction, then I get a one-dimensional Schwarzian action. And at the point we parted yesterday, we were discussing whether all the off-shell solutions are included in this field redefinition. So what we realized over lunch was that's not the case. I am actually parameterizing only the solution space or the on-shell space of the 2D Liouville theory, and the fluctuations, the off-shell fluctuations are indeed suppressed, but even otherwise, since even in the classical limit, I am restricting myself to the submanifold of on-shell solutions of the 2D Liouville theory. Okay. But so which is to say that from the 2D Liouville theory, I am only looking at the on-shell solutions, but from the 1D,
because the way you've written that solution e to the minus phi in terms of f of z,
yes,
that is a solution for
yes,
any of f.
yes,
Okay.
yes, indeed.
Okay.
But from the one-dimensional point of the Schwarzian theory point of view, I've still not taken the classical limit, and the one-dimensional Schwarzian theory is still indeed a full quantum theory of these f of sigma modes in one dimensions, which are the reparameterization modes as we understand them. So
just to understand, so just for a moment, suppose theta was 0, then your action is just the Schwarzian. If you extremize it, you get only very particular functions f of sigma
yes,
as solutions. Are you going to say they will lift to the corresponding f of z's, which are again very special, and somehow you'll focus on those very special classical solutions? Or in other words, what will be the connection between the f of sigma, which solves the, say, equations of motion in the lower dimensional theory, and the original two-dimensional theory you started?
Big F is holomorphic, so
Big F is
yes.
sigma, then it will have an analytic continuation.
It will have an analytic continuation. But is there something special about those analytic continuations as opposed to any
From
of
the
z?
Liouville point of view. From the Liouville point of view.
That, just to ask. I mean, or just to get the connection right, is there some kind of collective? I mean, what is
It seems
It, yes,
thing in
yes.
which these are the low energy, low cost fluctuations, this little f of sigma fellows, and there are other solutions which correspond to the orthogonal modes to the solitonic degrees of freedom, and he is ignoring them because of some classical limit taking this b equal to 0. So, but within the low energy fluctuations also, of course, you can look for what's the lowest energy of them. So, and that would be this SL2R degrees of freedom. I mean, without the theta term, it would have been SL2R. And
No, but why is this action not, if I write Schwarzian of tan of f,
yeah.
won't I get this?
Yes, this is still the full SL2R thing. So
This f prime is not a perturbation over Schwarzian. This is
Oh,
no, 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 yeah, yeah, it's still not
you can
the,
absorb the theta
yeah,
inside the
yes,
that's what I mean.
yes. So
because I know that without the theta thing there, it is the solution is another SL2R in which you say f is equal to tan
Right,
phi
that is when
by
theta equals 1, but now
oh,
I
you
can,
just redefine beta to be
yes,
beta by
Yeah,
theta.
yeah,
yes.
exactly,
Oh,
yeah.
I'm so stupid. Yes, okay.
Right, but when theta is not equals 1, I'll have an additional term which will indeed break the SL2R to U1. So I'll just come
So
to that on
1
my
minus
next
theta
slide.
square thing. Okay, is
No, that 1 minus theta square thing is precisely what,
went into
yes.
that.
So I again forgot to write this connection between the capital F and small f here. So it was like this. So capital F of Z at say I'm restricting myself to tau equals 0. Okay, this was e to the power 2 pi I over beta times f of sigma.
We cannot absorb theta into beta because the limits will be very large. Ah, that is true also. Yeah, that's correct. So
I can
but somehow you're saying there is this action as it shows up here
right.
as an SL2R
Yes.
thing.
But basically, what I mean to say was that the temperature, effective temperature with this theta not equals 1 will be some scale temperature that I'll see later. So, yeah, as in when I start doing the calculation of the correlation function, the theta absorbed into beta is like, okay, I have a new temperature in which the background temperature is like the probes see a temperature which is a scaled version of the background temperature.
But this action as it stands has a silver.
Yes, but the point is I have still not done things consistently because this is only coming from the bulk part of the action. This is still a boundary term, and I'll still ask what happens to the boundary term. I mean, I still have to include that, so that will be a theta dependent term. Okay, so
You should go on, of course, but just to understand, so from now on you'll analyze this one-dimensional.
yes,
And at the end you'll come back to what it's teaching us about the Liouville theory we
no,
started with?
no, I will not do, but I will indeed use the Liouville, means I'll find out a way of expressing the one-dimensional observables as correlation functions in the two-dimensional Liouville theory, and then separately take a classical limit of those correlation functions, which will make certain calculations which are computation of certain observables easier, because I didn't know how to compute them in the Schwarzian theory.
Okay, so just to rephrase, just so I get it right, you might have wanted to study this one-dimensional theory anyway. For example, it's the boundary theory in the JT model.
Yeah.
Up to after some tan whatever you get the extra term, let's say, and so that's what you're doing. And it's interesting that it can lift. At least the solutions of this theory will lift to the sum of the solutions of the higher D.
Yes.
But
Okay.
I can see one advantage. You might have said that Schwarzian is already embedded in SYK. We know that. You know, so therefore, why not use just SYK? But SYK is not a Hamiltonian theory.
And SYK has much more stuff at higher.
So does this. So does this. The 2D Liouville has much more stuff.
Oh, 2D Liouville.
Yeah, because and you know he is giving us a field theory in which unitary field theory in which SYK is embedded as a low energy or low cost part of the thing, like the solitonic part, like pion part, and he is ignoring the mesons, which were the other massive mesons, which we do also in SYK, but SYK is not a unitary theory because
But is the original Liouville theory unitary?
Yeah.
How do you know?
I'm working with C greater than 1. Sorry, yeah, C greater than 1 theory.
C greater than 25.
25, yeah.
That proves that it's
He's positive, even this.
unitarity mean here you mean the scattering amplitudes are all unit? Is that what it means?
Yes, yes.
That's been calculated.
Not,
Norms of states are positive.
Norms of states are positive.
yes.
If a Hilbert space is positive. That's known, I mean,
Yeah.
it's well quantized.
Yeah,
That's the statement in the quantum theory.
right.
Is known to be.
These complex anomalous dimensions don't come if C is greater than infinity.
But I mean, is that enough? Just to understand.
Okay, is that enough? That
I think so. No. Well, not just the central charge, but
you also need to know that the lowest highest weight is not not less than 0. So that's one, the typical Liouville theories of C less than 1 have that thing. As a result, it is non-unitary.
Yeah, but in this
I
case
thought that problem was not there.
yeah, that problem won't be there here.
So we know the entire spectrum of states here in the case
Yes.
of quantum theory.
Yes. We know even all the 3-point functions, and
There are
we
also these, just to understand, you must go on, but there are also these whatever brain states and all that. All of that is
Yes.
known. The whole spectrum is unitary. Okay, very impressive. All right, I see. And in some limit, you get this basically the Schwarzian theory, which is on the boundary of ADS2.
yes.
And so in that sense, it's embedded in an ultraviolet computer.
I
Yes.
mean, the embedding does not need random averaging over any noise, which SYK has.
Yes. But then that we kind of knew, because I mean, even the Schwarzian theory, as we know, it comes from various different UV completions.
Yeah.
So, which don't necessarily have random sum over.
Schenker makes this point about random averaging and etc. etc. Here is a theory which does not have any random ensemble thing. It's a one particular theory. Yeah, maybe that could be a difference.
This is supposed to be generic feature of conformal field theory at large central charge that the Schwarzian should come out or not. Or is it specific to the this is
No, I don't think so. So here it's kind of coming.
This is a very interesting question, I feel.
yeah, from the point of
Yeah,
view of
very, very interesting. Because, just sorry, but just to, very sorry to interrupt, just from the point of view of if you have an extremal BTZ black hole, we expect this theory to come out, but the question is, what all is needed for that, you know? Is large central charge enough, or, yeah, sorry, go on.
So the argument that is made in one of the Verlinde papers is follows this, that the Schwarzian can be understood as the character of just the Virasoro block. Like
Is that right?
yes, and in this 2D Liouville theory, you are restricted as long as you have one Dirichlet boundary condition. You're restricted to computing that character of the Virasoro block.
sorry, what is the statement I missed?
So the Schwarzian is it can be interpreted as like the Schwarzian partition function is the character of the Virasoro block, which happens so because of the presence of the Dirichlet boundary in this two-dimensional Liouville theory.
I mean, we can discuss later what I think would be a concrete calculational thing to do, which is, I mean, you can do the 4-point function calculation in the ADS2 theory, where the time reparameterization mode is exchanged, you know, the Schwarzian mode is exchanged. And the point is, from the underlying CFT2, how do you get this 4-point function? It seems clear that basically a Virasoro block is being exchanged. But what does it take to say only that block will be exchanged and everything else can be ignored? Is it just large central charge and
Large
low
gap.
energy?
Large central
Yeah,
charge,
large gap and low energy. Can you just prove it with that or not?
Yeah, I think as far as just exchanging the Virasoro block is concerned, I think having a large gap and large central
Isn't
charge.
it? So I need to talk to you about it, because this has to be formed. It's not been formed up in the literature, I think. That
But I don't understand the latter part. Where you
Can
say
you
that
just
is equal to
just one small thing to add, which is the extremal BTZ is not the vacuum of the CFT, but it's the a state which carries some charge, you know, and so enough charge so that Cardy's formula applies for the state counting. So we have to do the argument that the Virasoro block is the only one in the context of that state. But okay, yeah, probably I think let's just stop. I think you probably have.
But how is it that the Virasoro block is supposed to be? Why is it expected to be this thing?
Ah,
Question.
so
How about this breaking of the Virasoro symmetry present to R? Isn't this the concept of that?
The Schwarzian action.
So how do why should I expect it directly to correspond?
so one way to see this is when I have a Schwarzian path integral, what I have is basically e to the trace of e to the power minus beta L naught. because the Schwarzian integral of Schwarzian is L naught. Okay, and in the classical limit, I can say that the trace of e to the power minus beta L naught is same as the path integral over the phase space.
Okay.
Uh,
But still, why is it equal to the Virasoro?
Sorry, you're right. I don't have a full answer, but roughly speaking, isn't it because the SL2R part of the entire Virasoro annihilates the vacuum, and here also, if f of sigma lies in SL2R,
then yeah.
you get 0. So isn't that why the map probably is between the entire Virasoro block, and this is that it's a non-trivial states which correspond to something like that? Okay, but I don't know where Herman gets that statement.
No, that is exactly why he's saying that, because when you're taking the trace only over those states in the identity block.
Okay, so we just, I mean, this has not been formed up in the, this is an important point I feel you can just form.
But actually, in the context of BTC and the Brown-Hino, the tower of the backbone was given by the Brown-Hino deformations, which were characterized by one anti-holomorphic function and another, holomorphic function and an anti-holomorphic function. So that the corresponding TZZ is the Schwarzian of that, and TZ bar Z bar is the Schwarzian of the anti-holomorphic guy. And Rohan did this calculation here of how much is the cost of this Brown-Hino deformation in terms of action. So it was some square root of the anti-holomorphic Schwarzian times the holomorphic Schwarzian times the anti-holomorphic Schwarzian. That's the effective action of these things that you get there. It was all only states created by stress tensors. So therefore, it.
I think there should be a way to once you identify the holomorphic and the anti-holomorphic part, that product of square roots can be just one Schwarzian.
Yeah, I think you're just saying, I'll give you one small piece of evidence in support of that. If you just look at the free energy, above extremality, so you take the extremal BTZ and you just heat it up a little bit, you get a free energy. We know from the ADS2 region that it comes entirely because of the Schwarzian. And if you ask in the underlying CFT2, where does the free energy come from? Let's say the extremal state is because you excited left movers and not the right movers. So L0 is non-zero, but L0 bar is 0 in the extremal. Then the free energy comes from exciting the right movers, the other sector, as you know very well, at small temperatures. So it roughly seems to be that it's the Virasoro block corresponding to right movers, but acting on this non-trivial state, not the vacuum, but the state which carries the charge, which is carrying the entropy. So I also don't understand Rohan's calculation, but the thermodynamics shows that very clearly.
Yeah, I think the dimensional reduction that you were doing is something which is not. I mean, for example, we did 3D, Kalsa-Klein thing from 3D to 2D. There we found that the time reparameterization modes are not the Brown-Hino guys. There are some normalizable deformations which correspond to fluctuations of the bilocal, as one would expect. And so I'm a bit confused about how to see it from 3D to 2D. Maybe there is a way of seeing it from 3D to 2D so that this thing comes out.
Just wanted to say, you should go on there. I mean, what Pranjal is trying to do in a sense, I feel is very well motivated in the following sense that we know examples where ADS2 emerges from ADS3, which is the BTCs. And so there must be a sense in which from at least 2D CFT, whether Liouville, I don't know, but say a large charge, large gap CFT in an appropriate charge sector, you must be getting the Schwarzian region. I mean, we know this phenomenologically in string theory. So the point is just to understand that, and I think that would be very nice.
Some kind of
where one left or right movers, whatever. Anyway, please go on.
So Right. Now I'm interested in computing certain observables in the Schwarzian theory, and when I say that, what I mean is I want to compute some correlation functions. So, but correlation functions of what operators in the Schwarzian theory? Now, Schwarzian theory by itself has only non-local operators in it, because if you are on a particular orbit, which, so the naive one that we know is diff S1 mod SL2R, we want operators which have the same symmetry, like which are SL2R invariant, and the operators that we know of which have these SL2R invariants are kind of these kind of 2-point functions, bilocal operators. You could also generalize to write down trilocal operators, which are the reparameterized 3-point functions of 2D CFT kind of thing, and also like any higher point function. But the simplest ones are and I think the only ones studied till now are the 2-point functions. And I want to understand if I can compute the correlation functions of such bilocal operators from the Liouville point of view. Okay. I know that these bilocal operators have an understanding as correlation functions of, say, some fermions or some other local operators from the UV complete theory that I started with. But since I'm not interested in what theory the Schwarzian is coming from, I'll just treat these bilocal operators as the standalone operators in the Schwarzian theory, and that's why I would also allow it for an arbitrary weight of the bilocal the L here can be arbitrary. I don't restrict myself to the weights allowed in the SYK model. Okay. So what I find is that the vertex operators of the Liouville theory are insertion of vertex operators basically corresponds to the insertion of bilocal operators in the dimensionally reduced theory. Okay.
So minus sigma is the image of sigma, is that the point?
Yeah, okay.
Why
Minus sigma is the image of sigma, and that is coming from the doubling trick, because one local insertion in the upper half plane has a Z star insertion.
Z star translates to minus sigma.
Yes, because Z was tau plus plus I sigma, so Z star is, yeah. So but once I write down my path integral and everything, I know that my path integral is translationally invariant, so I can actually move it to anywhere. So this is like just coming sigma minus sigma is only when I'm just deriving it from the dimensional reduction. Okay. And also, as I was just saying, that there's an additional boundary term in the 2-dimensional theory which imposes the boundary conditions on the Liouville fields, and that boundary term so that boundary term, and let me just remind you what that term was. So it was very naively a vertex operator insertion in itself. I mean, it's kind of an exponential of a vertex operator, right? Right. So this in the 1-dimensional theory, after using the periodicity of or the monodromy condition on these capital F fields, I can write this boundary term as just a local insertion in the 1-dimensionally reduced Schwarzian theory. Okay. So just like to conclude, if I do it for all the different kinds of boundary conditions that I can impose, then the dimensionally reduced actions are given by these particular actions. So like for example, the Dirichlet boundary condition has the Schwarzian action with this theta equals 1. I should not have written a theta there, because that corresponds to Dirichlet, and then that is the well-known Schwarzian theory that we at finite temperature with periodicity beta. Okay, and the orbit that I am integrating over in that case is diff of S1 mod SL2R, because the whole SL2R is still the symmetry. But in the other cases where I have at least one of the boundaries condition to be normal, then that boundary term that I was just showing basically introduces a term which breaks the SL2R to U1 because that's a single derivative term here.
Just out of curiosity, if you've thought about it, in the context of the JT model, can you get this boundary action by doing something other than Dirichlet boundary conditions for the dilaton or something? Just, if it's an aside, don't worry about it.
Yeah, I have not thought of it. Yeah,
Very
but
interesting.
that yeah
I don't know how to get those other actions.
yeah.
Yeah, there is this boundary version of the ESCFT, right, which Tadashi did, and this by looking at the near intersection unit of M to M5, and so if you draw a boundary, I know for 2D, 3D, I mean CFT2 to ADS3. So if you draw a boundary in ADS, the two-dimensional CFT, the corresponding bulk is something in which the boundary, you just extend the boundary straight on along the holographic direction. So that's like the half of the Poincare ADS. And this several calculations have verified this, but I don't know whether it is universally accepted or not. So this is a boundary version of ADS. So that might be applied.
Yeah, but the other thing direction
That is for ADS3
CFT2, but and the boundary is in that direction that you would Kaluza-Klein reduce, right? You're thinking of the boundary in that direction, which in your language, like you're Kaluza-Klein reducing.
No. It is in order to get to your stuff.
Yeah.
In CFT2, I can take Euclidean CFT2. I can take any of the x or y equal to 0 to the boundary, and then you just extend that line, okay, to into the for any value of z, and that's your bulk. It's half of Poincare thing. So and now you have some y equal to in the 2D Liouville. So let's say you start with your 2D Liouville. So there also you have y equal to 0, let's say, as your boundary. Then you know in the one higher dimension what is the geometry to look at. But after you dimensionally compactify, I don't know how the
Liouville is so you have to first reduce on the time so that you get just the quantum mechanics in the sigma direction, and then the sigma has the boundary, right, which is this boundary term.
Yes.
So you're doing it in 2 steps. The ADS3 you're looking at a slice, so that it's JT gravity corresponding to fixed T, and which so the boundary conditions from above should drop down to become some boundary conditions.
corresponding to fixed T. Yeah, because it's a time independent thing, and yeah, I need to draw these things to
Anyway, let me just make sorry.
Yes.
One which may not be totally wrong, but there's a whole story waiting to be developed, I feel, which is the analog of the Schwarzian theory for ADS2. Namely, you have a much wider class of attractor geometries which you get in gravity than just ADS2. And for example, you have Lifshitz fixed points and all kinds of other fixed points where the neo-horizon geometry has a scaling symmetry, but it doesn't have SL2R. And it will be very interesting to see if there is the analog of the correspondence between the JT model in ADS2 and the Schwarzian theory in these cases. You wouldn't expect an SL2R, but some version of diffeomorphisms on the boundary.
Yes.
So that's
That could
partly
be.
why I asked. It will be very interesting to see if you get some structures like that.
Yeah.
In this near-Rosen limits, these geometries are something 2-dimensional times in sphere.
Yeah, something two-dimensional times a sphere or some plane or something. It's a product. Often, yeah, sometimes, yeah. So we will have to study it, but okay. Anyway.
That actually sounds more promising than what I was just thinking after you asked it, which was to say that maybe I could change the boundary conditions on the higher dimensional theory, because as you remember in our work we saw that it was just the k phi term, like the Gibbons-Hawking term of the higher dimensional theory which gave rise to the Schwarzian, and asking how can I modify that term. So that basically requires modifying the boundary conditions of the higher dimension. But this definitely looks more interesting than yeah.
But it might be worth playing.
Yeah.
Where the denominator is not changing to U1 because of the boundary term, right? That's just the whole bulk that is preserving U1.
Yeah, that's what I was thinking. Ultimately,
Yeah.
because it's 2D, there's no bulk dynamics, and you can write it all as a boundary. That feature will survive from 2D gravity, but just the isometries will not be NSL2R work.
Yeah.
Go ahead.
Okay. So till now what I've done is basically shown you how to arrive that there is an equivalence between the 2D Liouville theory and the like its dimensional reduction gives me Schwarzian theory of different kinds, let me say, on or Schwarzian theory on different orbits, but this still like does not give me a well defined prescription of how to do calculations or compute the correlation functions. So next what I'm going to do is just give a prescription of how to do the calculations in the two dimensional theory, and by dimensional reduction we already know what that would correspond to in the modified Schwarzian theories that we just derived. So the idea that I use is that instead of doing the calculation of on this open string, I use the open closed string duality of the Liouville theory and interpret these boundary conditions of the open string as some states in the closed string language. And now in this closed string language I also have a consistent Kaluza-Klein, like the actual spatial Kaluza-Klein reduction. Okay. So in that case the correlation function computations of the Schwarzian theory basically basically boils down to computing some like expectation values on this closed string between some boundary states. Okay, and these boundary states are well understood in the Liouville theory, in sense that given the what boundary conditions I impose in the open string picture, I know how to write the corresponding state in the closed string picture.
Sir, could you not have obtained, so from this point of view, you cannot obtain Schwarzian on a round circle or compact circle? Yes, you need to work on an interval.
Oh, despite the fact I'm working on this, since I did the doubling is what gave me a Schwarzian on the round circle.
Okay, but then in the previous slide you have these boundary terms which are what? It is thing is on a it's defined on a circle.
Yes.
So you just a bulk insertion.
It's an insertion at some point on the in the circle. Yes. Okay, so means these boundary states are well understood in terms of superposition of the Ishibashi states, which are the conformally invariant states in any 2D conformal field theory, and the wave functions that are required in the superposition for precisely the Dirichlet and the Neumann, the states corresponding to the Dirichlet and the Neumann boundary conditions were computed by Zamolodchikov and Fatih Zamolodchikov in their papers in early 2000s. Okay, so these are precisely the wave functions corresponding to the two kinds of states that we are interested in. When I impose the Dirichlet boundary condition, there are a more general class of states, but those are not the ones I'm interested in, and we have still not thought of whether there could be any interesting thing there. But so yeah, so basically what I'll be so now the whole prescription is, if I'm computing the correlation function of bilocal operators in the Schwarzian theory, then I should look at this this particular like evolution scattering amplitude, and have certain insertion of local Liouville operators on this cylinder. Okay, and if I compute that and take the classical limit, that the b going to 0 limit, then what I get is the correlation functions of the bilocal operators.
But if you do this with the boundary conditions, can you get to this thing?
This one?
Yeah.
Yeah.
No,
Oh, previous. Sorry.
Yeah, so that if you do this with the Neumann boundary condition, you already have these insertions there, right? F prime.
Yes.
So in that sense, it will calculate your point function with those two insertions.
Right. Yes. So if, in the case when I'll be having these FZZ boundary states, so if I have only one to be FZZ boundary states, that will and the other one as ZZ boundary state, then that will compute the Neumann-Dirichlet case in this previous slide with only one insertion. And if I have both to be FZZ, then it will be the second one.
But I see. But you are interested in putting in some insertions by hand also, right?
Yes. So those insertions by hand are the insertions of bilocal operators, which correspond to additional insertion of vertex operators on this cylinder.
Some specific.
Yes.
Yeah, those insertions are boundary condition changing operators, which you must put on the upper plane, because otherwise the entire boundary condition would be one uniform thing. So when you want to flip from Dirichlet to Neumann, you must insert something in the origin. And Neumann to Neumann with the same R, I wouldn't expect that you need anything at all.
Yeah, but I'm doing the more general case in which the two Neumanns, the two FZZ wave functions are different here with different parameters. Yes.
Sorry, I thought you were talking about the bulk insertions, right? Some insertions in the
Yeah,
bulk.
but he's talking about the boundary. So what he was saying is this corresponds
That
to
corresponds to that.
boundary changing insertion from the two-dimensional point of view.
So this same safety function was derived for theta equal to 1.
Oh no, this is for arbitrary theta. So now here this S parameter is again related to R. So the S parameter that appears here, PS, P times S.
Oh, P times S.
Yes.
Oh, P times S.
Yes. So this S is like I times theta. Yes. No, I didn't understand what you. I mean, it's just a different parameterization of those states. It
You're
does.
saying overall it should have been a phase. That's what you're saying.
It does. So since even if I wrote down in terms of like my theta was allowed to be complex and imaginary. So sorry, imaginary and real.
Yes.
So it's just sometimes it's a phase, sometimes it's a decaying. So fine. So like now this like concludes my setup of what the technologies I'll be using for my computation. So now before I go on to compute things, let me just tell why and what I'm trying to compute. So since I wanted to verify extended eigenstate thermalization, let me just recap what eigenstate thermalization states. So the statement of eigenstate thermalization is that if I measure an operator in energy eigenstates, then to the leading approximation it is given by the microcanonical expectation value along the diagonal terms, with some corrections which are suppressed by exponential of entropy. Okay, right, and like I have such a behavior of operator expectation values in energy eigenstates, then I can show that a generic excited state this operator would thermalize in a generic excited state by dephasing arguments. Okay. Now, what extended eigenstate thermalization means is it extends this definition of ETH and says that if I am there's a more general class of operators which, when measured in energy eigenstates, also thermalize, and they should some different properties of thermalization consistent with directly working with a thermal ensemble. For example, in this paper, what they conjectured is, if I measure an O-talk in pure states, then the O-talk itself will show an exponentially growing behavior corresponding to some Lyapunov index, and in a theory which is like holographic or maximally chaotic, this Lyapunov index would precisely be given by 2 pi by beta, where now this beta is the temperature corresponding to the equivalence of ensembles given by the energy of the eigenstates. Okay.
Is there something more general in which instead of an operator like that, you talk about all local operators in a certain subregion, and therefore you talk about the reduced density matrix taken in a pure state and claim that that can be approximated after that e to the power minus s by 2 by a reduced density matrix in a thermal ensemble.
Yeah,
that
that's
would cover it all.
sorry, yeah. So there is that's called subsystem eigenstate thermalization, and in 2 dimensions, Shavik and his collaborators, Shavik Datta,
Yes.
they have been studying that for quite some time now. So even that was first conjectured by Hong, Toliadimarsky and Nima Lashkari, and since they are the ones who have been studying eigenstate thermalization in conformal field theories for a long time now.
Yes.
So, but yeah.
Well, if I go to the operator product expansion
Mm-hmm.
of this 4-point function, which is in 4 operators that are inserted in the middle,
Yeah, here.
then once I get to the level of 1-point function, I can use the ETH
Mm-hmm.
and write that as a thermal expectation value. And now, can I not go back to just show that this should work? This should just mimic the thermal expectation value of this whole topic.
Yeah, but then even in that case, won't I have some? It's not just a simple 1-point function, right? Like every time there's a sum over different operators, like sum over various thermal expectation values.
So maybe I cannot do OPE because it's some out of time order thing. But if I could, then I could reduce this to a sum of a whole bunch of operators.
Yes.
For each of them using that ETH, I could write as thermal expectation value.
Right.
And now I can restate, go back and say that this is equal to the O-talk in the thermal state.
Is that line above only for energy eigenstates or?
This yes, but
No, the O can be
O can be.
no, even O needs to be like it's not necessary that a theory shows ETH for all classes of O. In particular, like for the O should not be extensive operators.
But I guess, okay, just to maybe Abhijit is saying, suppose for a moment it was true for all operators, then from there could I prove the O-talk?
Basically, I had an issue with the word extended. It seems specialized because there is no state. Is there a statement about off-diagonal terms?
Here the statement about off-diagonal terms is precisely that they are really small.
Below.
Oh, yeah, even here the statement is that they will be suppressed exponentially in entropy.
I mean, the lambda L growth will be true for the diagonals and not true for the subdivisions. dependent exponential.
Right,
in the-
yeah.
Is that the claim that, or is it just that the coefficient is
I can commit to the coefficient being
Okay,
suppressed,
okay.
not the time
Okay.
like
Yeah,
behavior.
Then it does seem like you just take that, go to one point function and apply this.
I'm still not sure because sum of various thermal expectation values need not be thermal by itself, right? Naively. May, right? Uh,
Okay, we could talk about it.
yeah, maybe. Okay. So now I'll move on to actually computing what I'm interested in computing, which is some correlation functions with this setup and technology. And I'll do both some first let me start with some semi-classical computation because they're easier to follow and slightly more intuitive. And then the exact calculations we already know is some computations in the two-dimensional theory, so that's okay. But so say let me start with the computation of one point function of a bilocal operator. Okay, and what I'm saying is I want to measure one point function of the bilocal operator in some energy eigenstates of the Schwarzian theory, which I define as the states for which the Schwarzian expectation value is constant. Okay, and so
there are such states.
yes, yes. Uh, in fact, you could do again a rewriting of the Schwarzian theory so that it appears as a free theory in one dimension, and then these states are like constant momentum states of those uh, uh, like fixed momentum states of that free theory. Okay.
This capital F is the same as small f? Is it right?
So since I'm working with zero temperature case, in that case, yes, capital F is same as small f.
In the semi-classical limit, you are right. These states exist.
Yes.
They exist even away.
Yeah. So
I believe that the energy operator in the two-dimensional theory on a particular time slice would be just the Schwarzian.
yes, it is.
Energy
Yes.
operator in the
Yes.
Liouville theory.
Yes. And I'm also interpreting the Hamiltonian operator of the Schwarzian theory to be the Schwarzian itself because
That's
yeah.
the only SL2R, the only thing you can write in diff S1 mod SL2R, the simplest thing. So that's in fact true.
And it is also the generator of U1 transformations on the manifold as we know it from the Stanford Witten paper. So from that, as in it's the one that generates some shifts in F fields on the
Anyway,
man.
the underlying reason is
Yeah.
this is the simplest thing
Yeah.
you can write down. So
Okay. So now for the so the
No, it's a chapter. So if the action is the Schwarzian, the monodromy.
so in the semi-classical limit, I found I want to find out the configuration of f of sigma, which has this constant, and so I solve for this Schwarzian derivative of f of sigma equals constant solution for this, and that corresponds to the tan transformations. Okay, the solution for this equation is, and this is precisely the transformation which we use to take a Schwarzian theory on a line to Schwarzian theory on a line to Schwarzian theory on a at a finite temperature with the temperature corresponding to this square root of 2e by c. Okay, so
Now your theory has this additional pieces, right? With those additional pieces, the Hamiltonian is still Schwarzian. Oh, so you will redefine this new temperature and write it as tan again.
no, I'm still, so for now I am working with my orbits of diff mod SL2R, so I don't have those additional terms yet.
okay, can I just ask something, not to slow you down too much? I mean, is it clear how to quantize it? I mean, I'm just asking, I mean, so you go to the conjugate momenta, but then you have 4-time derivatives and this and
The
that.
classical Noether charge. indeed happens to be
Classical, I
the-
understand, but if you're going to say the full, I mean, the quantum theory, you have the following spectrum. I'm just asking, I mean, does one know how to quantize it exactly and make this statement beyond the semi-classical? I'm just asking.
What?
Or you don't, you say, well, we just assume there are, whatever is the full quantum version, there are eigenstates of this operator.
Yes.
I think you were doing it from the two-dimensional point of view, isn't it, or not?
No,
I
right.
mean,
This is all in one-dimensional.
At least
So
the statements.
but according to Stanford Whittle again, the quantum mechanics of the Schwarzian theory doesn't make sense because it doesn't have a Hamiltonian. The path integral makes sense. You can compute it by localization and so on. But that path integral cannot be interpreted as trace of e to the power minus beta. Because it has some finite partition function which is weird with a continuous density of states.
So I can't think of it as a quantum.
That's what.
The quantum.
However, he has another handle, which is the two dimensions.
I understand, but all these statements here
Are
about
the
any
one
eigenstates, then in that 1D,
Yes.
wondering what is the meaning of that?
Then this confuses me, the statement that this is equal, the partition function is equal to the character of the Virasoro block. Then I could just define the states to be the, L
Yeah.
raising operators acting on the vacuum. Solve the states in the block. So how is this consistent with things being
The
finite?
division by SL2R, which makes it finite, with that you can't treat this as e to the power minus beta L, because you need the division by SL2R to make the partition function finite. This is what I understood.
But when you consider the states of the block, I mean, all those are killed by Z2R.
Trace, you need a trace of e to the power minus beta L, right? So you need all the highest order states to be.
No, I mean the states in the Verma module of the L0 itself. Then you would not have states corresponding.
The vacuum character, you're talking about the vacuum character.
Yeah. In that module, you don't have SL2R states corresponding to the SL2R transformation.
That's where you can do that perhaps because the vacuum is killed by SL2R. But the point is that you would like to interpret the path integral to be a thermal trace in which all states are there. So how is that? How does that have an SL2R thing as a zero mode theory? Because the whole path integral is supposed to have a division by SL2R. Trace doesn't seem to naturally incorporate that. Character does. So somehow you have to, indexify or some such thing to make that into just the expectation value of the backbone.
Okay, anyway, please go on. Yeah, okay.
Okay. So right. So at zero temperature, if I'm on this if I'm interested in this particular orbit, then my bilocal operator in terms of the F fields is simply given by the reparameterization of the zero temperature 2-point function, right? And now if I'm computing,
Now you have generalized from sigma and minus sigma to arbitrary
Yes,
sigma 1 sigma.
yes.
2, yeah?
yes, okay, and I'll compute this. So if to compute this correlation function, I'll compute this on this particular F configuration, okay, and what I get here is
The semi-classical.
it's semi-classical limit, okay, and in that case what I get is thermal 2-point function, a correlation function that I can identify as thermal 2-point function in one dimension with a temperature corresponding to the one given by which is a temperature which is proportional to the energy,
Right.
square root of energy.
Okay, but how is this showing eigenstate thermalization in that don't you have to take it for M and N and then etc. etc.
Good, that's a good. So in this work, I have all till now only worked with the diagonal elements and shown that the diagonal elements correspond to the thermal expectation value. And I agree with you. It's very important to show that off diagonal terms are suppressed exponentially, which we have not done yet.
How do you do this semi-classically? Because this would want F, this would want F prime.
I'm sorry. Can you say again?
The off-diagonal ones.
I think yeah, offline ones are not so clear.
So semi-classically it's not, but I think I can modify the exact calculations in a manner which I can. It's not straightforward, but I think it is doable. Yeah. Okay.
So we start with maximum temperature of 0.
Yes.
And yet this shows that certain object is thermalized.
Hmm.
But in typical quantum mechanical systems, we don't expect that to happen.
That's thermalization hypothesis.
But that already actually, that's the thermalization hypothesis already assumed some background temperature.
No. So here also I'm not assuming any background temperature.
But you do expect it only to happen in a sufficiently complicated quantum system. So
Not something that's integral.
correct, right. A few degrees of freedom or something. But I think here his large central charge or whatever, that is the analog.
Becomes a complication. But somehow, even though you evaluate the expectation value in the microcanonical ensemble, there's an effective temperature that you read out from that. That's this beta.
Yes. Yeah. I mean that's kind of an equivalence of ensembles. I can.
By the way, how do I see the degeneracy of at energy E, the entropy?
At energy E there will be, so energy E is related to what I was saying, that if I interpret it as constant momentum states in the free theory, which I can actually do a rewriting of Schwarzian. In that case, they are just twofold degenerate like this. So Ek is given by k square by 2c, where the c is the Schwarzian parameter, and then given an Ek there is a plus and a minus momentum states.
But you do expect a huge degeneracy, right?
Why is that?
I mean, at energy E, you would expect a lot of degeneracy, no? Only two states.
Yes. Why maybe I'm missing why you are expecting
If I
it.
may re-ask, I don't know, I think this might be what Abhi has in mind, that if you want to compute the free energy, the value of the on-shell action,
Right.
how would you see that it has the required entropy, from there? That might be one way to ask it. Then wouldn't the answer be that at energy E, in the semi-classical limit, you'll take the solution f of sigma which you have written down, put it into the action and evaluate it, and if you interpret that on-shell action as the free energy, you will get the entropy
Yes.
that Cardi tells you,
Yes.
right?
Yes. And your question is how is that consistent with this twofold degeneracy?
Yeah, I mean, I'm just trying to see what this additional piece is after E to minus S. What does it satisfy?
Yeah, I'm similarly
It'll probably be
confused.
that kind of.
If in the 2D, if it is like a free particle quantum mechanics, then the degeneracy is just 2 per momentum. So then, unlike in SYK or some such thing where you have large n. So the thing is, because of large n, sorry,
Yeah, no, yeah.
please explain.
Sure.
Like if this was k1 square plus k2 square up to kn square, then of course you are counting the volume of the shell, and that's huge in the large
Yes.
n
You must, so we are supposed to look at it as, if I take a generic state,
Me, that's how you usually define a microcanonical ensemble, because if even for a quantum mechanical system, that's the way you're saying it,
so
right?
those separations will be related to a typical state you would choose. Right now, there's no that is just not considered, so you won't see it.
What do you mean?
So
I mean, the number of delta E just includes, it's a free particle thing. It's just one-dimensional free particle motion, and I'm not drawing any energy shells in some huge dimensional phase space.
that's how usually I interpret eigenstate thermalization, because otherwise I'll always, like, if I'm in a very simple quantum mechanical system with discrete energy states, okay, or even a many body system,
Okay.
there'll be, like, at a given energy,
Right.
there'll be only a few number of states exactly at that energy. So the way I define a microcanonical ensemble
Right.
to define even to state my eigenstate thermalization hypothesis
Yes.
is by considering an energy shell.
No, I agree, but I'm saying that, there's a large central charge.
Yes.
So there might have been a microscopic theory
Right.
which led to this thing,
Yes.
and there I could see some huge entropy.
Yes.
But once I have reduced to a Schwarzian theory, which you say essentially corresponds to E equal to k square, okay, there's just one-dimensional energy thing, so there is no entropy there. I mean, there's this little bit of entropy.
No, in Schwarzian theory also I can construct some state psi like this C E E, coefficient C E and get E. This would be a state, and I would arrange the coefficients such that it's mostly centered
That's
around a
about
particular
that's
E
about
body.
normalization. No, wait.
No, no,
In a Schwarzian theory,
summation C E.
you can take linear combination of energy eigenstates
Exactly.
also.
So you'll have to take it from a particular band. That's it. In your spectrum, you'll have to take a state from a particular band, and and you'll have to see how the energy spread is. That spread delta E relates to the off-diagonal separation. That's where the entropy will come from, right? You'll have to, unless you have used these in the C, you won't find the entropy there.
That's the point. This huge density of states,
Yeah.
sinh of square root of E and so on, which Stanford and Newton get. Okay. Where does it come from? So, okay, good. Where
I
do we
see.
get this huge density? This density of states here is delta A is equal to k dk.
I think I agree with what Gadde just said then, that I define my entropy to be the one, like in the semi-classical language, to be the one given by. So in terms of such an understanding, like there's an implicit understanding that there's a UV theory this is coming from, and it always implies that the degeneracy at any energy is given by what I would obtain by computing the free energy. Maybe that's the right prescription of associating entropy with at any energy.
See, for delta k, delta x, there is one state. Okay. Now let us say your two-dimensional theory does have some x. Okay. So therefore there are whatever number of delta x's you can fit in L. So L by delta x number of states per delta k, and then we can just count. So per delta E. Okay. That's it.
Some,
No.
as he's saying, it's some microeconomical entropy. So you
Never mind.
Yeah.
Doesn't matter. Okay, I can see the point now. Probably what Ved is saying, and you are also saying that there is a huge density of states, rho E going as sinh of square root of E.
Yes.
Where does it come from? If that is the model, E is equal to k square.
So I'm saying, I'm prescribing as an ad hoc thing right now.
Yes.
That this is the model with understanding that the degeneracy is not twofold here,
Yes.
but it is always associated by computing the free energy, by looking at the classical configurations and computing the classical partition function, and associating the entropy that I get at an energy from that free energy with these states.
That's all mathematics, but I'm saying, is this the Hamiltonian or not?
If I
E is equal to k square. If that is the Hamiltonian, I know what the density of states is, square root of e to the power half.
Right.
I mean, the partition function from this Hamiltonian won't also become such, right? It's some e to the
Yes.
power minus beta k square, which I can
Yes.
integrate.
No, I'm saying to go to the more basic thing. Density of states rho of E, okay, that is dk de is equal to 1 over k. 1 over k is the same as, sorry, what? dk de, yeah,
But
dk de is the same as 1 over k, that's e to the power minus half or some such.
But that's not what.
That's not what it is. So what's going on now? Now I'm confused about your 2D way of landing at the Schwarzian theory.
from the 2D perspective, you would claim that this is the right spectrum, right? I mean, you would claim that the k dk e that comes from here, the rho that comes from
Yeah.
this energy spectrum is the right spectrum.
Now that's e to the power half or e to the power minus half. I'm getting from here, right?
Yeah.
Yeah.
At every delta k, there is one state. Okay. Per L, of course, you have another dimension. Maybe that is doing something. You know, maybe that effective length of the dimension that you're compactifying, that has something to do with E.
That capital C is a by b squared.
A by yeah.
Capital C is what?
A by b squared.
And this yeah.
But that's something finite. But let that be. I can put that in my calculation. So it's e to the power minus half. Yeah, I mean energy to the power minus half times C or divided by C or some such thing. What
It's not minus half plus half, right? You want dE by dk.
I want dE by dE by dk is the number of so number of
Number
energy,
would be the
energy
inverse.
level
Yeah.
density would be dk by dt.
Yes. Yes.
It's like dn by dt.
Yes.
And that's 1 over k. So that's e to the power minus half. And that's it.
What is e to the power minus half?
The density that you get from this
Yeah,
one
it's 1 by
dimensional thing, it's 1 over k. That's the same as 1 over square root of e.
Yes.
That's it. That's rho of e. Where do you get sinh of square root of e from? Which is the density of states. Short. I mean, this is not the density of states of the Schwarzian theory. Compute the path integral, do the inverse Laplace transform, whatever you get is sinh of square root. That's supposed to have that should have a two-dimensional interpretation in the way you were saying it, right? In fact, that would be the right answer to Stanford and Witten. That here it is. We have something from which we can get this. Anyway, let me not. Okay, so we went into this detour because Sandeep asked about all that.
Yes.
And then we asked about how large it is.
Yeah.
Okay.
Okay. Now if I want to do the calculations on these different these other orbits, which is diff S1 mod U1, then the corresponding states which lie on these orbits are given by taking an energy eigenstate that I defined previously and acting on it by some local insertion of exponential kind of a vertex operator, right? Like, because from the two-dimensional theory point of view, I had the boundary term was e to the power
And the path integral
Yeah, e to the power 5 by 2. So
So this new is
sorry. I thought it was e to the power f prime.
yeah,
So
f
actually,
prime was when I from the Liouville theory point of view,
okay.
it was e to the power r times e to the power 5 by 2.
Oh, yes.
double exponential.
Yes, that's why when the v is like a vertex operator. I mean, it's not precisely a very like mathematically accurate statement, because that one insertion after from the one dimensional point of view, as you just pointed out, gave me only one insertion, which was like, so the doubled insertion on the Liouville theory correspond to one local insertion on the Schwarzian theory, right? So it's kind of a square root of vertex operator in the exponential, but let's not go, it's not mathematically precise, but I know how, but that does not stop me, because I know how to what happens when I'm on this orbit, like for a state corresponding to this orbit in the semi-classical limit, the bilocal operator has the corresponding scaling with theta on the background temperature. Now the background temperature itself is set by the energy of these eigenstates. Okay, so now when I'm in these different orbits, in that case I see an eigenstate thermalization where the temperature is given by a scaled version of the temperature corresponding to these energy eigenstates.
So now what are we calling as the background temperature?
So I'm saying that the energy eigenstate E sets up a background temperature.
So that was your previous calculation.
Yes, and
This
the
is just
presence.
a parameter which would be the ensemble equivalent of micro ensemble.
Yes.
So okay, you are thinking of doing this calculation in energy eigenstate with this extra insertion.
Yes.
So you are treating what is already present, that is the energy eigenstate, as setting up the background.
Yes.
Earlier
And
there was no such thing. You were directly taking the whatever vertex operator created that energy state.
yes.
into the calculation.
Yes.
So the background temperature was 0 and there was an effective temperature.
Yes.
Square root.
Yes.
Now there is one extra complication.
Yes. So the role of this guy in life is to take you to a different orbit instead of the S1 mod diff S1 mod SL2R orbit. Okay. So that's about bilocal 1-point functions. Now I want to do a OTOC computation in the energy eigenstates, and I want to so OTOC is like a insertion of bilocal 2-point function with the legs of the two operators interchanged. Okay, so the technique I use here is I look at the Alexey-Shatasvili symplectic form on the corresponding manifold, okay, sorry, the corresponding orbit, and this symplectic form corresponds to a Poisson bracket of f on that manifold, okay, which is given by this Sinch expression. Okay, so the commutator of f of sigma 1 with f of sigma 2 Poisson bracket is this. Now what I say in
Has this in the formula? You calculated
this
expression?
oh both these expressions come appear in Don Jajot's paper.
Ah.
So
Because I can recognize the box thing from Alexis.
actually you shouldn't, because
that doesn't. So what's missing?
this term is not there in Alexey-Shatasvili, and that is precise. That's because the energy, the
Oh, yeah.
that's
Oh,
not.
I see. There is some delta T naught wedge. Oh, yeah, indeed. That term is not there.
Yeah, that parameter is not there when you are restricting yourself to your given orbit,
Yes.
because your T naught, the zero represent T naught is the zero representative, and that's not changing.
Nice. I see. So it can. That's the one. So thing, parameter which marks which
orbit you are on.
Okay, good, nice, nice.
Okay.
So the small f you're using is that tan.
Yeah. Yes. Okay. So yes. So now the thing that the idea that I'll be using is the OTOC corresponds to interchanging the ordering of the second time of the first bilocal operator and the first time of the second bilocal operator, right? So I have an ordering which is T1, T3, T2, T4. Okay.
So you're calling sigma time now, is that right?
Yes, yes. So I've analytically continued. I want to do a Lorentzian computation. So yes. So and in the semi-classical limit, I can compute. So I'm not writing it explicitly here, but now I'm interpreting this bilocal insertions as formally as actual 4 insertion VW VW. Okay, and to compute a commutator like this, okay, V commutator of WV and then W.
This is
4-point function.
Oh.
This is a commutator. Right? This is the kind of thing I want to compute. Okay, and for that I.
So that just cancels the one part, is it? And you define.
Yeah. So I want to commute the f of t2 with f of t3. So that I can do by taking taking the derivative of the bilocal insertion with respect to local f of t1 and f of t3 and multiplying it with the Poisson bracket. So this is like the semi-classical computation of the difference between time ordered and out of time ordered correlation functions.
This is just a way of saying V.
This.
So let's say V own O2W.
Yeah.
Just remove O1 and O2 and put the commutator.
Yes.
That's what that's.
Yes.
The derivatives are removing the things in the middle.
Yes.
Just inserting them.
Right.
Just the Poisson bracket itself.
Yes. So it's, and in that case what I find is because of the presence of this particular commutator, I find an exponentially growing behavior with time, and where the Lyapunov index is given by whatever the effective temperature is for the external states in which I am computing this OTA.
What happens to the, where do these two parameters R and the dimension of your operator enter? They do. So
R is related to
R
theta.
is theta, and the bilocal dimension. Bilocal is this thing, right? The one you showed before, the kind of bilocal you defined for.
Right, the dimension appears somewhere, but like it appears in this part of the expression. I am just looking at this part because I want to look at the late time behavior. So there is some multiplicative thing. So this.
All you have to look at is the Poisson.
Yes, I want to look at the growth. The Poisson bracket defines the growth and the rate of growth. So, I mean, of course, there's some multiplicative part to this. This multiplies something which I'm not writing here.
What are the states that you're considering to get that Fox expression?
Yeah, so I'm saying that these states could be either these E states or E of R states.
But that box guy is for E of R, ER states.
Yes, but yes, for theta equals 1, E of R is E. Because,
R equal to 0.
sorry,
Theta equal to 1 and R equal to 0.
R equals square root 2.
But then that boundary term is still present.
But the boundary term is still present, but you can show that even for the 2D Liouville theory, R equals root 2 corresponded to, it imposes the same boundary conditions as the Dirichlet boundary conditions.
One of those degenerate vertex operators.
Yes, I think, yeah. I don't remember exactly.
It's
Let me
already
not
bounded
commit to
down.
this.
Now you
Yeah.
might get some total derivatives from phi.
I
And
that
those total derivatives will have root 2 as its coefficient, so when this r is root, it might cancel.
let me
That's what
not
I meant.
commit to the detail here,
Yeah.
but yeah.
Alright,
So it was sigma 1 minus sigma 2, the Poisson bracket, and if you make sigma 1 into I T1, the sinh, how come the sinh remains sinh? You are doing FT1, FT2, FT3, sorry, FT2, FT3 Poisson bracket. So
Yes.
you should take the F sigma 1 as a F sigma 2, F sigma 3 Poisson bracket and replace sigma by IT, you know?
Oh, I get ETH depending on my choice of theta here. So if theta is
So normally if you just do that replacement, you
yes,
get sine, right?
yes.
And now you say that, wait, in that expression, where is theta? Oh,
Theta is T
just
naught.
T naught, okay.
T naught was theta square by 4.
Okay. Now, if theta is, so that thing, that square root of T naught needed to be, needed to have an I to cancel the I coming from sigma, I see.
Yes.
So theta needed to be, therefore, the purely imaginary stuff.
I think I messed up this. This should be sine here, okay, because this I gets change this sinh into sine, and this theta is there. So when theta is imaginary, that's when I see an ETH. When theta is not when theta is real, I don't see an ETH.
I see. I see. So a sinh of 2 pi times imaginary theta
Yes.
times d23.
Yes.
I see. So as a result, you say that the hyperbolic operators, I mean, yeah. So
The hyperbolic orbits thermalize while the
hyperbolic orbits thermalize.
elliptic orbits don't thermalize.
Yeah. I see. Cool. And where do you see the thing that this Lyapunov growth goes only up to t equal to log n or log c here?
This is there's a 1 over c here.
Oh, when you bring back, so in other words,
OTO
when you
is
bring back that
this
inner
minus
order
this.
thing, there will be some 1 plus.
Yes.
Yeah.
Something like that,
That's
right?
what
That's,
Yes,
that's
yes.
what it is. And then when that catches up with that 1,
Yes.
Log C.
nice.
Yes.
Very nice.
Okay. Now, yeah, exact calculation. I just wanted to show you more for an illustration purpose for the how the what the expressions for the exact calculations are, because then you can see how that facilitates even the computation of quantum corrections here and not just the semi-classical limit. But yeah, so using the trick of that the open close string duality, duality that I described previously, and replacing the boundary states of the boundary conditions of the open string with some states in the closed string, I can write this Schwarzian path integral as as some expectation value of vertex operator in the closed string picture.
This is the exact means what? Without going to the classical limit? Is that
Yes,
what you mean?
yes.
But then you are back to the 2 dimensionals here.
No, because without going to the classical of the one dimensional theory. So I am taking B going to 0, but I am not. So there was.
Oh, so you have some the scaled version of B, which is not.
Yes. So my Schwarzian theory had a parameter which was A over B squared, right? And this is C going to infinity is what decides the classicality of the Schwarzian theory.
Okay, it's like alpha prime, and it's like Tuft coupling.
Yeah.
small.
Yeah. So with the knowledge of the wave functions, so when I'm doing it between the Zamalachak brains, which corresponded to the thermal, just the simple thermal correlation functions in the Schwarzian theory, in that case, using the wave functions and the time evolution operators, I can compute this expression and I get an answer like this. Okay, this
In
is
the computation, what you have to do is you have to write down an action,
yes,
and then you have to write down the specific wave function arrows.
yes,
The boundary
yeah.
wave functions. And
I can do the standard two-dimensional. This is standard correlation function in 2 dimensions. So I start with a wave function, evolve by certain time, insert this operator, and since everything in the 2D Liouville theory is known, so I can compute this.
So the ZZ brain corresponds to the energy eigenstate in a semi-classical computation. Is that
Uh,
the analogy you're trying to make, or
The ZZ brain in the one-dimensional computation corresponded to no insertion at all, and the size of the open string was twice the size of the open string, was same as the temperature of the one-dimensional theory.
right? But so this exact computation, what is the analog in semi-classical computation of this brain?
I don't have.
You don't have.
Yeah, in that was a semi-classical thing. So that is taking this exact computation and take the large C limit of this answer.
And this would give what answer? The what is that? The thing that was sandwiched between two
E.
E's.
Yeah, yeah.
No, so what's the answer to this question? Are the ZZ states are energy eigenstates or not?
No, ZZ states are not okay.
These states would be the caps on the cylinder.
No. So the ZZ states are the caps on the cylinder
Closed string picture, right?
in the closed string picture. But if you have ZZ states, then that corresponds to a thermal correlation function in the one dimension theory. But I can extract out the energy eigenstates by projecting out just one energy eigenstate from the ZZ wave functions.
So summing over all the energy.
Yes.
Because it's like the Calabrese-Curry states. Calabrese-Curry states are not energy eigenstates.
No, what is like Calabrese-Curry state?
This ZZ states.
Yeah, but in the one dimensional picture,
Yeah.
ZZ doesn't have no insertion. So if you remember, with the ZZ insertions, I get just this path integral with some operator insertions.
So it becomes like a vacuum.
It's yeah. I should
It's
really put theta equals 1 here. Yeah.
Not just the vacuum, right?
No,
You get
No, not the vacuum. It's a finite temperature. It's a thermal ensemble.
Sorry, it's a finite temperature thing.
and the temperature, you read the energy from that temperature. Where
So
temperature is.
I am actually indeed. So when I'm doing a ZZ thing,
Is it?
Your beta is given,
yes.
and you are reconstructing a microcanonical ensemble from that beta.
I will do that. I'm still not. So for the time being, I'm actually doing an honest to goodness finite beta computation.
Yeah.
Yes.
Good, I see.
Whereas your semi-classical computation was in the micro.
Yes. Yes. But there's a way to extract that expression here. So I'll just come to that. Okay. Good. So I just to specify here, like from.
There it is.
Yeah, but then I'm not doing it from this point of view that you are asking. Like I'm extracting it. I'm looking at the answer and extracting out that the density of states can be interpreted as sense here. Okay. The propagators here. So this is some Feynman diagram I drew. Right. The propagators are given by these exponential factors in this expression. Okay. And here you will see that the propagators are indeed like e to the power energy times time, like the duration of evolution, and that energy is precisely this k square by 2c now. Okay, and the vertex factors are given by these gamma functions. Okay.
Yeah, so there is a degeneracy in saying.
There is a degeneracy, but that's not like what I was saying was I can deduce a degeneracy, but if I rewrite the Schwarzian theory as a free theory, I don't know how to.
I know this. I know this.
Yes.
This is what Gervais had discovered. That Liouville theory can be written as a free theory with E equal to k square.
Yes.
But the Poisson bracket is not trivial.
Uh-huh.
See, I was thinking so far as delta t delta x has only one state. No, that's not correct. X comma t Poisson bracket is not one. I remember this.
Right.
This
This is
was
correct.
discovery.
Yeah.
You can make it a free particle at the cost of introducing some complicated Poisson bracket. So the Poisson bracket will have that information about the same.
Yeah.
Because if it is delta x delta p, you cannot get it. Okay. I see. All right.
Okay. And like now if I take the semi-classical limit of this expression, this complicated integral expression, which is the exact one point function of the bilocal operator, then I indeed get a thermal correlation, thermal expression with the temperature beta, which is the temperature for this theory. Okay. Now as you were asking how to extract out the pure state. So to extract out the pure state, so if I naively take beta going to infinity limit, then I will get just the vacuum expectation value. Okay. But I can take beta going to infinity with some projectors, and what I mean by saying that I have projectors is one of the two, so on this, say this particular arc, okay, which corresponds to the R integral here. So here this R integral corresponds to sum over all possible states on this line, okay, and P integral corresponds to sum over all possible states on this line, on this propagator. And okay, so I'm saying that on one of the propagators I integrate only over energy eigenstates with energy greater than some value k. Okay. And now if I take the beta going to infinity limit, which is to say that I am extending this length of this propagator to be infinitely large, then I won't project down to vacuum now. I will project down to the states corresponding to k.
Minus k square with that beta thing.
Yes.
You read out beta in terms of k.
Yes.
Got it.
And right, so I get precisely the same beta effective temperature that I got previously.
But isn't there something more simpler, like you compute the energy density in the k state
Mm-hmm.
and determine the energy density of the ZZ state?
Mm-hmm.
Just compare the energy densities. You'll get in the ZZ thing, you'll get something in terms of beta, 1 over beta square or whatever it is. And here in the k state, you compute the energy density again. You'll get something in terms of k. Just equate them. I presume you'll get the same stuff again here. You see what I mean?
Mm-hmm. No, can you say that?
You want to say that what's the ensemble equivalent? What's the microcanonical ensemble equivalent of a canonical ensemble given by beta?
Yes.
One way to compare them is to compute the energy density in both
Yes.
and equate them.
Yes.
That's one way in which you can get the T is equal to square root of E.
Yes.
In the other previous case. And here you will get this expression beta equal to 1 upon k.
Yeah.
I think you will get from that calculation also. Just compute the energy density like the Schwarzian
Yes.
in k.
Mm-hmm.
Oh, what are you saying? How do you do this? I mean, I don't know how do you do this.
Define the expectation value in the k state through this procedure.
Through this procedure, yeah, through this procedure. But here your observable is much more complicated than just the energy density. The energy density would be the Schwarzian of F, and or even total energy, because you are just interested in comparing one number here and one number. Integral of the Schwarzian. Sorry, no, there is no integral. There is no space. It's only, yeah. So just the Poisson bracket of f of sigma in the k state versus in the ZZ state. But how do you compute this in the k state? Is that the
The K state is precisely this Poisson bracket that I wrote down here. This is a semi-classical thing, right? Like
this is a semi-classical thing, yeah.
so this is commutator, quantum commutator measured in some state. That state is where what.
Okay, so here you have it. So then this is
But
in microcanonical.
Yes.
And you do the same computation of expectation value of this Poisson bracket in the ZZ state. And compare these two.
The ZZ state will have beta, whereas this will have that
E.
Yeah, that's right. That's what I'm saying.
Yeah, but that's still a semi-classical computation. I'm doing it like a.
Oh, I see.
I'm claiming that I can do an exact computation here.
Oh, I see. Okay.
This is an exact expression of this correlation, this operator expectation value in this K states here. Okay, and then I took the large C limit to compare it to the answer that we previously. I also know the exact answer. That's the point.
So taking beta to infinity is setting the background temperature to 0.
Yes.
But you have kept the E state.
Yes. So there is an E induced temperature and then there is the background temperature. Yeah. Okay. Now I want to do the bilocal 2-point functions, because again I want to compute
I have the cutoff at 12. But, go on.
This is I'm almost towards the end of it. Like so basically I can take the let me go directly to OTOX. The OTOX, I can compute the OTOX in the ZZ states. Okay. So OTOX in the one-dimensional theory computes to out-of-time ordered insertions in the ZZ states, which corresponds to basically insertion of an R matrix, which twists the from the two-dimensional point of view, this R matrix interchanges the ordering in, say, just the holomorphic part, but not the anti-holomorphic part. Okay, so that only two of these guys are exchanged, but these bottom two are not exchanged. Okay, so this it's the R matrix basically relates the correlation function in the S channel and the T channel. So using this expression, I can again take the classical limit of this expression. I can again use the projection trig, compute it in energy eigenstates. Okay, this expression in energy eigenstates, and then take the classical limit, and I again find precisely that the Liouville exponent agrees with the temperature given by these energy eigenstates. Okay. Another new computation that I do is compute a 2-point function of heavy light operators. Okay, with this particular configuration, I have heavy insertions separated by half the circle size, beta by 2. Okay, and in between I have some light operators, and then I take beta going to infinity here, so that these heavy operators correspond to some creation of certain states. And what I find is that before I take beta going to infinity, the temperature as perceived by these light operators, light bilocal function, is the temperature is bigger than the background temperature. Okay, so that means that heavy operators are exciting the states. Okay, and the increase in so the effective temperature is also proportional to the weight of the heavy operators, which is what I expect in eigenstate thermalization. but the effective temperature itself is proportional to the background temperature, which means that if I remove the background temperature, the effective temperature is not there. So, this is what we call weak form of eigenstate thermalization. So, for these particular operators, I see eigenstate thermalization in pure states.
So you are saying no matter if I put a heavy operator on a vacuum,
Yes.
so vacuum does not create any background.
Yes.
So if I put a heavy operator on a vacuum, the light operators cannot see any temperature.
Yes. Heavy operator on vacuum at infinities. There is another calculation that where you have the heavy operators at finite finite distance, not at infinity, and you have light operators inserted between them. So, for just for technical reasons, we have not been able to compute this configuration. In this configuration, we expect there should still be some finite temperature. Then the reason is because there is some kind of a factorization that happens when you take these insertions to infinity. So, yeah. Yeah.
But in this Kaplan papers, don't they have that, or they also have a similar result that?
That's in 2D CFT. So, this factorization works differently, slightly differently in 2D CFT. In 2D CFT, if you
there it would work, right? That the heavy operator
Yes.
on a vacuum will generate some temperature.
yes, yes.
And here, what is the background temperature beta for one of beta?
What do you mean? What
is
T is?
What T is the background temperature?
Yeah, it's a background temperature which is the size of the circle.
Which you are taking to infinity.
Later, yes. But if I can keep it finite also. So, I am saying that if I keep it finite and compute this this particular bilocal 2-point function, then the expression of this bilocal 2-point function is similar to the expression of the bilocal 1-point function at finite temperature with some beta effective or effective temperature which is different from the background temperature.
But you said you were not able to do that calculation where these are at finite separation.
At 0 temperature and finite separation.
Oh, you keep them fixed but not proportional to beta.
Right. So, I am doing this configuration where the separation of heavy operator is beta by 2. So, I can always take beta going to infinity. I am taking beta going to infinity with this separation kept fixed, sigma 1 kept finite.
But if you also keep that separation fixed between heavy operators and then take beta to infinity, that calculation is
Yes. Yes.
So what is the expression for the beta effective?
Actually, we computed beta effective numerically, so we don't have the beta effective everywhere.
But you can
So
see this much that if
yes.
initial beta was infinity, then
Yes.
beta effective is also infinity.
Yes. So, it's something like T effective is T times L heavy by C upon some 1 plus some number times T, and there is another number here. So, it is of this form. So, basically the temperature, effective temperature goes like this for with L heavy by C. Okay, where this here it's starting at T background. Okay, so when this weight is order 1, then it's background temperature, but then it increases and saturates to something.
It's not like that square root formula.
No.
The mass of the
No,
relative
it's
vacuum
different,
is
yeah.
square root of 1 minus h
No,
divided by 24c or something.
Something like that.
no. Okay, so finally I can do this same calculations in the FZZT between the FZZT brane, which corresponds to, in the one-dimensional picture, just one insertion of that f prime exponential f prime of f prime operator, right, which I am calling the FZZT operator.
So that beta by 2.
Yes. Okay. and what I find is that if I do a non-homogeneous finite temperature computation, then presence of this operator insertion changes the temperature by a multiplicative factor theta. Okay, and again depending on what orbit you are on, like whether theta is real or imaginary, you will see thermalization or you don't see thermalization. And you can also do the OTOC computation, and then you see that the Lyapunov exponent also again becomes theta time the background temperature. Okay, but exactly like I'll just admit that we have not done an exact computation where we have scaled beta going to infinity and with a projector, so that I have ER states. So I don't have an exact computation of ER state expectation values. Okay, so just to summarize, these are the results that I presented at the start of my talk. Like for different states, I have for pure states I have eigenstate thermalization. For coherent states, I have thermalization depending on what orbit I am lying on, and for these operator states there is only some weak form of eigenstate thermalization. Okay, thank you.
How many papers is this?
This is all one paper. Apart from some results also appearing in the first paper that we wrote. But the first paper is mainly about conformal ETH.